What's up? So, in this video, I thought I'd walk through my custom base64 implementation project that I was working on because I've pretty much finished it. There are a few things that I want to maybe improve. First off, I want to write a test suite in PyTest because right now I'm just testing by randomly sampling different input combinations and verifying that my implementation matches that of the base64 standard library. I could probably do it more elegantly if I figure out something with PyTest. Additionally, it seems like my implementation is slower than the base64 library. I'm not sure by how much. However, when I was testing the output with images, it was pretty slow. It was like several seconds per image, and I'm sure that the base64 library implementation is probably faster. So something I might do in the future is do a time test of my method versus the default method to see how much slower my method is, and then maybe go back and see if there are any obvious optimizations I can follow. I said in the previous video that I wasn't interested in optimizing it too much, more just getting the implementation correct, which it appears that I've done. And I'm not going to get too into the weeds doing optimizations either. But if there are apparent optimizations to make, I'm going to try to look back and make them. But basically, what I started with was I did a bunch of reading up on UTF-8, on base64, and on Unicode, just to familiarize myself with all the concepts that I would need to build out this project. And I did a bunch of different things in this Jupyter notebook, basically just testing stuff, familiarizing myself with the bitwise operators and how they work. And eventually, you can see here, this is the class that I wrote. What I decided to do, and I actually have a separate file that I'll walk through, but it seemed to me that the best approach to take would be to create a class and then use class methods just like the default library does. So rather than having to instantiate a base64 object, you just have a base64 class that has callable class methods that you can call without instantiating an object. That seems the clearest way to do it for me. It would be to tie both the encoding and decoding functions to a single class rather than have them just be two separate functions in the namespace of a single .py file. Regardless, though, let me see if there's anything else in this notebook I wanted to talk about, and if not, I will. Yeah, let's pop over to my implementation. So this .py script is the cleaned up version of what I ended up doing. So I have a class with some class attributes, and then I have two class methods, so for the encoding and the decoding. Um, I'll start first by talking about these attributes. So I just mapped out the base64 characters with a dictionary where the number from 0 to 63 maps to the correct character. And then I also wanted a decoding table where if I had the character, I wanted to go back to the number which mapped to it. And so I just did that by taking my original dictionary that I constructed and reversing the keys and values. And I learned this as well when I was working on this, that if you have this class method decorator, that's what allows you to call a method within this class structure without instantiating an instance of that class. So I can just do custom base64.base64 encode, and this CLS parameter acts like the self parameter. So if there's any attributes in here, like these encoding and decoding tables, I can reference them down here with CLS.attribute for whatever attribute I'm looking into. So the first thing I looked for was I wanted to see, well, I'll talk about the encoding first. So the first thing I wanted to do was see how many complete groups there were and if there was any remainder. So basically with base64, you take bytes in groups of 3. And so if you have something, if the number of bytes modulus 3 is equal to 0, then you don't have to do any extra logic. But if you have a remainder of 1 or 2, you have to do a couple extra things involving padding to handle that 1 or 2 bytes that you can't group into a group of 3. Because what you do is you take 3 bytes, which is 24 bits, and split it into 4 groups of 6 rather than 3 groups of 8. So first thing I do is I see how many complete groups of 3 I have, which is what I'm calculating here. And then for all of my bytes, I basically combine them together. So I use bitwise operations to load in zeros from the right. So 16 places, load in 8 places, and then no places here. And by using bitwise OR, I combine all three of these bytes together into one single stream of one single binary number, essentially, that is 24 bits long. And so it might not actually be printed as 24 bits because if it has leading zeros, Python automatically will truncate those or not display them. But what I basically did is I shifted all of these bytes into their place and then combined them together with the bitwise OR operation. And then what I did was I had this bit groups list and I append all of them into the list in a particular way. So I grabbed the first 6 by shifting with 18. So shifting, I believe this is shifting right by 18. So the first 18 bits in the sequence drop off the edge and we grab the first 6. And likewise here, we shift right by 12 and then we mask with this 111 binary number to only grab the current right 6 that we need. And it's the same idea here, where we shift right by 6 again, and now we grab just the group of 6 that we need for the third group of 6. So I'm using this binary number here with the bitwise AND to ensure that when I'm doing this shifting, the numbers that I'm recovering, the groups of 6 are the explicit ones in the order that I want. Because what I'm doing is I'm taking each group of 6 bits and I'm appending it into this bit groups list. I'm a little tired, so I'm sorry if my explanation isn't as clear as it could be. So here's how I'm handling the remainder. So there's really only 2 cases, so I just broke it up into 2 if statements. So if we have a remainder of 1, that means that we have 2 bytes. Or no, sorry, that means that we have 1 byte left over. In that case, you take the first 6 bits from it and you group that to a base64 character. Then you take the 2 remaining bits from that byte and you zero pad on the right, which is what's happening here. And then you use these 2 equals padding characters to indicate that of the 4 groups of 6, 2 were missing because we only had 1 byte left over. Similarly over here, if you have a remainder of 2, that means you have 2 bytes or 16 bits. So you're able to grab the first one entirely from among those 2 numbers. And you're also able to, yes, you grab the first 6 here, you grab the second 6 here, and so you should have a remainder of 4. So you take those 4 bits and then you right pad with 2 zeros over here. And then we're just using that same masking process again to ignore the leading digits and only extract the digits that we want out of this binary number. And so in this case, we append 1 equal sign to indicate that from these 2 remaining bytes, we're able to get 3 groups of 6, but there's 1 group of 6 missing, which is what that equals represents. And then here, what I did was I tried to map these bits in the bits group list, or they're not individual bits, but they're groups of 6 bits. I tried to map those to the characters in the base64 encoding. So remember, I made this table up here. Now, what I'm doing is I'm using a map over the bit groups iterable where I'm applying this lambda function to each index, where basically I look up that number's letter or corresponding ASCII character in the encoding table only if the character itself in the list is not an equal sign. Because if it's an equal sign, there's nothing that maps to. That's just a padding character. And then finally, I take all the contents of the bit2chars list here, and I just join them together into one string. So it's a no space dot join all of this. So at the end, we take all of our individual characters and we join them together into one single string, which is what you would do when you actually base64 encode something into a string. And the next thing I did was I wrote the decode method. So we want to see how many padding characters there are, because that's going to decide how far in the list we're going to traverse in our for loop. So I've got a list of bytes that I'm ultimately going to return, because the actual base64 implementation returns a bytes object when you decode. So you go back to the original bytes that you would have encoded in the first place. And so what I did is, and this is probably what's slowing me down, but this is the only way I could think to do it in the moment, is I basically am building one super long binary sequence of numbers where I'm taking in the characters and then I'm shifting them left, including the next set of characters, etc., until I've got a full binary sequence of all of the original bits which were present in the bytes object that we originally encoded. So the way I'm doing that is I iterate through each index of the string, but I subtract off the padding. So if there's any padding, we don't want to map that back to a binary number because it doesn't represent anything. That was a value that was missing, and so we had to pad it. And so what I do is I start out with 0, I left pad with 6 zeros, and then I use bitwise OR with the decoding table of the current index in the string to fill in that group of 6 bits. So the decoding table takes in the character and maps back to the number. So what I'm basically doing is I'm having one long um, binary sequence that I'm filling in by shifting to the left by 6 and then filling in the 6 spots that just opened up by using this bitwise OR. When that while loop finishes, what's left is we have to clean up the padding logic. And the way I did that is I wanted to figure out how many bytes were in that string, excluding the padding, right? So if there was no padding at all, that means that the number of bytes modulo 3 was equal to 0. And so what we do is we just take the length of our base64 string and multiply it by 6, because each character is representing 6 bits, and so that's just a straightforward calculation. If we have one padding equal sign, that means we had 2 bytes left over. And so I believe that's I always forget with this. I believe this is a right shift by 2. So we drop off those 2 padding bits that we had at the very end, and then to calculate the number of bits that were in the string, we take 6 by the number of characters minus the number of padding characters, and then subtract off 2. Likewise, you add 4 padding zeros when you have 2 uh, padding characters, and so as a result, you drop off those 4 with the right bit shift, and then you perform a similar calculation. And so in all 3 of these cases, what we get is we get this n underscore bits, which is the number of actual information bits that were in the original string. We divide that by 8 to get the number of bytes that were in the original string. And then for each byte in that original string, we're going to append to our bytes list, which is a list of integers. We append this binary sequence and what, or bitwise ANDed with a binary number of just 8 ones in a row, and then we shift right by 8. So what we're doing is I'm kind of going in reverse, where I'm taking the rightmost 8 digits, adding them to this bytes list, and then dropping those off, shifting, grabbing the next 8, etc., until we've exhausted the binary number and there's nothing else to grab. But if you notice, what that means is that we actually reconstructed the original bytes in reverse order, because we're going from right to left rather than left to right, which is how it's done in the encoding process. And so at the end, we have to reverse the list, and this is an in-place reversal. So you just call it here. And then finally, you're able to construct bytes objects from an iterable. So I just pass this iterable that I reversed, get the bytes object, and return it. And I'm going to put this code on GitHub in case anybody's interested in looking at it. I hope I did a decent job explaining it. I did this a couple hours ago and I'm pretty tired right now, so I think I might have stumbled over one or two things in the explanation, but generally, I think the way the code is written is pretty straightforward. And if you're confused about something, probably just write it out. Like these bit shifts are probably the most confusing thing to look at visually. Write those out on a piece of paper, and it becomes pretty evident what they're doing and why they're there. So I also wrote a testing script, which I probably should have queued up at the beginning of the video because the images take a while, like I said. I will start it up though. So this is already going to finish. This is testing random strings. So like I was saying in one of the other videos, Unicode has, or sorry, UTF-8 is an encoding scheme for the Unicode standard. And so since Unicode has millions of code points defined, what you have to do with UTF-8 is sometimes you have to represent those code points with 1, 2, 3, or even up to 4 bytes. And so rather than just using English characters, which are always represented with 1 byte, what I did was I defined the lower and upper bound of all of the Unicode characters which are defined. And I wrote this generate valid string function where basically you specify an arbitrary length of the string, and then it will randomly sample a code point between the lower and upper bound of the valid Unicode characters, convert it to a character, and then check if it's printable. Because not all the Unicode characters are printable, and if we tried to encode a character that's not printable, that might actually, I guess maybe it would work technically, but I don't know of a scenario where you'd ever want to encode a non-printable character. If you do know of a scenario, please let me know in the comments and maybe I'll add that. But eventually, you get a string, which is just a sequence of characters up to the specified length of unique printable, well, I guess not necessarily unique, but probabilistically pretty much unique, of unique printable Unicode characters. And what I'm doing is I'm taking in the bytes object, which you obtain by encoding that string, and then I'm encoding it with my method and the standard library method, asserting that the strings that result from that are the same, and then passing that string into the decoding method for both my implementation and the standard library implementation, and asserting that the bytes which are returned by both of our methods are the same. So those objects are the same. And so as we can see here, this is the testing logic that I've written so far. So I'm picking string lengths anywhere between 0 and 1,000, and I'm taking 1,000 of those such string lengths, and I'm running the assertion code on all of those. I used TQDM for progress bars because I was trying to figure out why it took so long for the images. For the images, I just took stuff from, this is the Flickr 8K dataset. That's not a very common dataset, or at least it's not one that I've heard of before, but it has variable size images. And so for whatever reason, if my method worked for some sizes but not others, I wanted to test that. And so I'm randomly sampling 10 values from that image data set, which should hopefully be different sizes. And so same logic, I'm just running the same encoding and making sure that it doesn't fail. And actually, I just realized I never wrote a string in case it does fail. I think it would have raised anyway if something went wrong, but I will just rerun the script real quick for clarity and peace of mind. So while I let this run again, I'll talk really quickly. I haven't scoped out what my next project is going to be. I think technically tomorrow, according to my list, I'm going to be reviewing my notes, which is fine. That'll give me some more time to think about what my next project would be. But if you guys have any suggestions, please let me know about anything that you think would be interesting or challenging or helpful to implement. One thing that I did consider, I was watching a video by this guy that works at DeepMind, or used to work at DeepMind. I'm not sure if he still works there, but he was saying that one of the things that helped him stand out in his interviews was that he would implement papers from scratch and then open source those implementations. And I think that would be great, especially for machine learning stuff that I'm doing. So maybe I could do one-on, one-off projects where one project I re-implement something from a machine learning paper. The next project I re-implement something from a core computer science concept, like I did here with base64. Uh, I've already done a lot of from scratch implementations with machine learning stuff. Like I've written transformers from scratch multiple times. I've written neural networks from scratch multiple times. And maybe it'd be interesting to make a video on that, where rather than just presenting a finished project like I'm doing right now, I split it up into a series and make it an educational sort of thing. Let me know if you guys think that'd be interesting, because I'm much more comfortable with the machine learning side rather than the theoretical computer science side. And so if you guys want any sort of tutorials on implementing some of these machine learning algorithms or implementing some of these neural network models, uh, it'd be a great exercise for me, and I think it'd also be a great resource for some of you guys out there. But yeah, I guess I'm not going to have a video where I'm sitting and talking to the camera, because this is already going on for a long time. But that's what the video tomorrow will be. And maybe in that video, I'll start to talk about some ideas for the next project and what that should look like. All right. If you stuck around through this video, thank you. As a reminder, I'm going to include the link to the GitHub repo on here for this code that I wrote. And additionally, I will probably make some updates in the future, at least regarding testing and maybe some optimizations. So if you decide to pull the repo remotely, just run git fetch every once in a while, or just watch the remote repo to see if anything gets updated. All right. Thank you all for watching. Have a good one.